Welcome back, Quadrature fans. My name is Marian Elena, and today we're going to do another geometry for Quadrature Cavalieri Principle Take 2. The reason for that is because I showed the first one to my brother and he did not understand it. In some ways it's a simple concept, but in some cases it's a difficult concept. Particularly we're talking about the slope. Anyway, so just like last time, we start with a box. Everything we do is a box, and this box has a characteristic diagonal, like this one, and it has another triangle here, and we're looking at slopes and areas. So ratio of slopes and ratio of areas. So let's look at that. All right. So basically, let C be the ratio of the slope of this, what I call MT, that's this slope here, to M diag, which is this slope here. The that's the characteristic diagonal. And let K be the ratio of the area of this triangle to the area of the entire box. So we are, in Quadrature, we are interested in looking at these ratios of slopes and ratios of areas, particularly because they're powerful and they tend to be invariant. But what's the purpose of this whole thing? Because that was befuddling to my brother and he didn't get it. Why am I doing this? Well, I'm doing this to show invariant principle. You know, you have a box and this is what you start out with, and then you do a shift. A shift like this. You hold this constant and you shift it. Imagine I hold it constant and I shift it. Just like a deck of cards, right? I have this thing and this is my deck. I hold constant, and this side I shift. And therefore, you know, we start out with 0, D, B, E, and A. After I'm done, there's no change over here. So 0, D, B, we keep these. I'm going to call this E prime. So you know, E prime, and A prime. And that alerts us to a shift, because we have done a shift. And when you do a shift, well, guess what? In Euclidean type geometry, this has stretched, it dilated a little bit, right? That's what happens in Euclidean geometry. Euclid has a ruler, and you measure this, okay, and then you come down to here, and it's longer, right? It's been stretched. Okay, but again, we're looking at the ratio of this slope to this slope, and the ratio of this area to this area here. Those are the things that we look at. So from you know, the original perspective right here, or straight perspective, we say, okay, C is MT over M diag, and that's simply, what's that? It's BD over BE, rise over run. That is the slope of this line. You see that? BD over BE. All right? And then what is the slope of this characteristic diagonal? Well, that's B over A, rise over run. Simple. You guys get it. Nice. All right. Say, yes, I get it.
Yes, I get it.
Got it. All right. Same thing. Now let's look at K. That's the ratio of the area of this triangle to the area of the box. Well, that's 1/2 of BD times BE, right? That's the area of a triangle. And the whole thing's over B times A. Rise, run. B times A. Pretty simple, right? No problem. Now we do a shift. What's a Cavalieri shift? Well, it's some kind of a change that we do, and we've done this. Okay? And in 1642, Cavalieri Principle, that was known that the area does not change. Why doesn't it change? Because the number of cards is the same. All I have done is rearrange the number of cards, okay? So the area here has not changed from this, right? Neither has the volume changed. Neither has the weight changed, the mass. So there's a lot of things that don't change. You know, if this was bread, the number of calories wouldn't change. So all of these are examples of invariant properties. Invariant, right? That's yeah, if you're Hungarian, you can say invariant. That's the right way to say it, right? Okay, nice. Okay, so let's see this. So we do a shift, and from a Euclid perspective, which that's where we tend to live. Everything is at nice right angles. There's perpendicular. That's the world that we tend to live in and think in. Well, the ratio of this slope to this slope, because I've shifted it to the point where this is totally flat, so this slope mt is 0. This slope here, yes, you can see that it's, you know, less steep, but you know, it's 0 over something, so the ratio is 0. Here the ratio was BD over B over B over A, right? That's the ratio. But things have changed from a Euclidean perspective. But, and of course the ratio of the areas is, you know, area of triangle, area of this rhombus, 1/2 BD times DE prime, okay? And we have to call it E prime and A prime because we shifted it. That alerts us. Euclid insists that we call it something else because this distance here is not the same as this distance here. It's been dilated. And Euclid insists that we call it, we label it a little bit differently, so I put the little prime marker on it. Well, okay, so the ratio of this triangle is now 1/2 BD times DE prime, that's this one, over B times W, B times W. Why is that? Well, if you take this triangle, put it here, it's basically the same, end up with this. That's basic geometry, B times W. But here's what I'm after, is that in affine geometry, I'm saying that not only is the area invariant, that's Cavalieri's principle, known in 1642, the slope is invariant as well, and that kind of blows the circuit breaker, but, you know, bear with me. You might say I'm a little bit crazy, but maybe, maybe not. Let's see what it is. Affine geometry. Affine, how do you handle that? Okay. From affine perspective, think of affine geometry as somewhat related to projective geometry. Let's say that we're looking at it from a spaceship. Let's say that you're Yuri Gagarin and you've got binoculars and you're looking down on this situation here, right? So Gagarin looks down from space and he's looking down and he sees this. What is the run of this? Well, it's DE. And he looks at the same thing over here, and what is the run of this here, it's d e prime, or it's the same thing. It's indistinguishable. If you look at it as a bird's eye view, satellite view, looking down, you cannot tell any difference, right? Of course, you can't tell what the height is because you're looking down. It's hidden from you, so projective geometry is not quite what we're after, but you get the point, is that the run is indistinguishable. Now the rise, no problem there. Euclid, affine, agree. This is the same, right? No, you guys don't have any problem. The issue is with this rise. And so what is the slope from an affine geometry? Well, it's the same thing. He can't even distinguish that there's a change. Remember, over here, the slope of this line is BD over BE. Affine geometry says, I haven't changed. I'm still the same. I'm BD, that's the rise, and look, I'm BE prime. Euclid says I have to call it E prime. Okay, fine. So anyways, from Euclid's perspective, this slope of this tangent, this slope here, it's the same, to him it's the same as this one here. It's rise, BD, same as this one. And what's the run? It's BE prime. He has to call it E prime. Okay, Euclid insists on it, but that's how he sees it. It's BD over BE prime. It isn't BD over DE prime or 0 over DE prime. He doesn't, no. It's BD over BE prime. Same as this one. That's how he sees it from affine. Okay, so that's this one. And then what is the slope of this diagonal here? Well, to affine, it's just B over A. Same as this one, B over A. Excuse me, it's B over A prime. He has to call it prime. Okay, fine. So we have this situation. Okay. Well, that's kind of interesting. Let's look at something. We know from Cavalieri Principle that areas remain changed, right? Unchanged, invariant. So this remains unchanged, and the overall area remains unchanged. Therefore, the K, the ratio areas, is also unchanged. That's an invariant property. And so this entity here, you see this? 1/2 BD times B prime over B times A prime must equal this. Because there is no change. This is Cavalieri says so, right? No change. And so what can we conclude? Well, this entity, 1/2 BD times B over B times A, must equal 1/2 BD times B prime over B times A prime. Well, we can cancel this out. And all we have left is BE over A equals BE prime over A prime. And the flip too. But look at this. This ratio BE over A, well, that's the same as, we just proved BE prime over A prime is the same as BE over A. And so we can write this as BD over BE over B divided by A. You see this? See this relationship here? That's this one. This one is equal to, so you can replace this with this. But now look, you end up with the same thing as over here. So what is that telling us? Is that the ratio of slopes is unchanged under a shift condition. Unchanged. I'm going to blow a circuit breaker, but yeah, it's in affine geometry. That implies that the slope is not changed, and that's that's hard to swallow, but it is what it is. You know, you look at this, and here it's different. You look at this, and if I shift it, it's different. You can say in a Euclidean type framework, but in affine, it's indistinguishable. It is the same. There's no difference. And so what we have is this idea that not only is area unchanged, Cavalieri Principle, but slope itself is unchanged. It's invariant. And that's what is needed for quadrature, and we'll show examples of how it's used. Maybe in my next video I'm going to drive it home. So in the meantime, my name is Marian Elena, and remember, before there was calculus,
there was quadrature.